This is Lab Report 1 pertaining to the concept of constant velocity. This lab is an observation of an object moving at a constant velocity along the x-axis. Throughout this experiment, we will be comparing the observed position of a soccer ball with the predicted position of a soccer ball as a function of time. We will look closer at the mechanics of Newton's second law of motion in order to create a plot of the predicted position over time. This comparison allows us to see Newton's second law of motion in action with a simple experiment. The general goal for this lab is to allow for a heightened understanding of the fundamentals of forces in physics, as we dive deeper into a real-life example of the concept of motion. Due to the fact that we were given the freedom to choose the object of motion, I chose a soccer ball to pose as the object. At the beginning of this experiment, I realized I would have to choose an object that would be able to roll smoothly with the least amount of friction with the ground in order to pertain to the subject of constant velocity, hence the soccer ball. As you can see in the video, the ball is rolling in the negative x direction as I had placed the origin at the center of the ball with the ball moving to the left. This means that the velocity will translate to be negative as well. Included in the video, there is a graph to the right that shows the position of the ball as it moves across the cement ground at a constant velocity. Although there was a contact force of push onto the ball, the initial velocity starts at a point where the force is no longer acting on the ball. Therefore, we can assume that the velocity is constant. With the data and information provided from Tracker, I was able to calculate the initial velocity of the ball. Based on Newton's second law of motion, I used the velocity update formula on the basis that the object is in constant motion. This means that the final velocity is equal to the initial velocity, rendering the net force to be 0 as well. Knowing that the initial velocity is equal to the final velocity, we can then rearrange the position update formula to find that the constant velocity can be found by dividing the change in position over the change in time. Using the ball's initial position at 0 seconds and the ball's position in the next frame, I calculated the initial or constant velocity to be negative 1.318 meters per second. However, it is important to note that there are a few minor assumptions to be made of the calculated initial velocity that may cause possible errors. One assumption that we have made is the assumption of constant velocity. Because the soccer ball is rolling along a surface that cannot negate friction completely, there may be a slight force in this experiment that we have assumed to be a net force of 0. Another assumption is that the points at which we chose to be the positions at each frame may not be accurate as it was picked by hand. Nonetheless, with the resources we have in this experiment, it is as close as we can get. Using the results from Tracker and an Excel sheet, it was easy to see that the observed plot of the position versus time graph was close to a linear line, but with the assumptions that we have made, it is reasonable that a perfect linear line is unconventional. We can see that the trend line is a negative slope due to the fact that the ball is moving in the negative x direction. Moreover, in the code you see to the left, I have updated some of the quantitative values such as the initial position and the calculated initial velocity as well, making sure the net force is 0. The main aspect that I have changed in this code is altering the code pertaining to the momentum principle. Specifically, I updated the code to reflect the velocity update formula and the position update formula. For the predicted position versus time graph, it was a clear negative linear slope as the points were calculated to be at perfect equal intervals through code. Because there is no net force and the change in position over time is constant, the velocity is also constant. In order to further explain the concept of constant velocity, I have plotted both the observed and the predicted position versus time graphs. As you can see, the velocity is constant. However, what you can also see is that the observed graph is slightly off compared to the predicted one. The experiment was a great maneuver to apply Newton's second law of motion as the curves seemed to be similar, reflecting the nature of constant velocity in real life. There are some questions to reflect upon as we went through this experiment. For example, what if we were to change the positive and negative axes? What would happen? Instead of the velocity going in the negative x direction, the velocity would go towards the positive direction. This would mean that the trend line for the graphs of the position versus time would be a positive linear plot rather than a negative linear plot. Furthermore, how does a computational model work? As in, how are we using a base in order to code our predicted graph? Well, the forces acting on the ball in motion include friction in the positive x direction. It is, however, assumed to be negligible, a normal force exerted by the ground onto the object, and the force of gravity acting downwards into the ground. With the friction being negligible and the normal force and the force of gravity being equal in magnitude in opposite directions, we can conclude that the net force on the object is 0. With a net force of 0 on the object, we can solve for the constant velocity by calculating the velocity at any point of the motion. In this case, we have used the initial velocity in this experiment.